All right, welcome back to Tollefson Physics. Now what we're going to do is we're going to look at a collision with these cars when they bounce off of each other. And so in these cars, there's little magnets on this side of the car, whereas when I push these together, they'll bounce off each other without actually hitting each other. We got that magnetic force that pushes them off that prevents them hitting each other. If I push them too hard, they'll crash and stop moving. And so this is known as an elastic collision. And so these magnets try to make this as elastic as possible. And so what we're going to do is we're going to do a number of experiments like we have done in other videos. And so once again, we're going to use photogates to measure the speeds. Now we're going to have to keep an eye on things. I'm always going to start this red car not moving, just to make life a little easier. And so I'm going to push the blue car into that. But what we're going to see is, because these have the ability to bounce off each other, sometimes I'm going to need to know the speed of both cars after they bounce off of each other. All right, so here's what we're going to start with. We're going to start with a stationary red car going and have the blue car pushed into it. And what's going to happen? Well, let's find out, right? Think about what you think might happen. They're both the same mass. All right, and so let's give this a push. Make sure it's on the track. Give it a push. All right, look at that. So the speed is nearly identical. So the blue car is the bottom one. It pushed it through at 0.46. The red car went through the other photogate at 0.44. And notice the blue car stopped moving. All right, so I'm going to try to draw my results on here based upon what I saw. So this ends up being the same size. So this is the final velocity, but it looks like it equals the initial velocity of the blue car. Right? So actually, how should I write that? So the final velocity of the red car looks like it equals the initial velocity of the blue car. And then the velocity of the blue car looks like it's 0. All right, so it stops. So that's interesting. So we'll think about why that is. So now let's see. I got listed here. I'm going to put 2 mass units on the blue car now. So I get double the mass on the blue car. Now let's think about what's going to happen. This has more mass. I'm going to give it an initial velocity. What's going to happen to that red car? Think about it compared to the speed of the blue car. And then what's going to happen to the blue car? Does it stop again? Think about it. Think about it. Okay. So if you have a prediction, let's actually execute the experiment. Let me put that close to the photogate so I get the most accurate results without too much friction. And so let's give this a push again. Boom. Okay, 0.49, and then that barely made it through. So I don't trust the speed. Now it's going backwards a little bit. But what did we see? What did we see? Well, the red car went faster. Right? So the red car went faster, but the blue car kept moving forward. So my red arrows are trying to show that difference, right? So the lighter car went faster and the heavier car went slower, but kept going forward, right? Let's look at that again. Let's look at that again. See if I can stop the experiment before the blue car erases my data. All right, so let's give that a push again. I'm going to stop it there. I would like to know the speed of that, but not right now. So I've got 0.47 for that car and 0.6 for that one. So this was going through here at I got it backwards. This was going through, the blue car was going through at 0.47, and it caused that red car to go faster. So that's what I've drawn here. We won't worry about numbers right now, but we'll talk about, why is that? Why is that? So I want to do my other experiment first, and then we'll talk about the why a little bit. So I'm going to move the mass over to the red car. Okay, so now the red car is 2 mass units, and the blue car is 1 mass unit. So now I'm going to push that through. What do you think is going to happen? Light car, heavy car. Opposite of what we just did. Well, that's why I set it up. Let's find out. All right, so let's give this a push. All right. So what did we see? We saw the red car go forward, and we actually saw the blue car go backwards. All right, but I kind of lost the data, so let's do that one more time. and look at the numbers. I'm going to stop the blue car before it goes through there so we can just look at those numbers again. So push, stop it. All right. So I push the blue car through at 0.56 and the red car is at 0.36. So definitely slow down. Okay. So how can we rationalize this experimental result? Well, it goes back to conservation of momentum again. So when I say conservation of momentum, I'm going to take all of the momentum that occurs before the collision and all of the momentum that occurs after the collision. So I'm going to add up all the masses and all the velocities before and all the masses and velocities after the collision. So let's just kind of think about that in a certain context. So in the first instance, the masses are the same. So I give the blue car a velocity. So I have the blue car is the only thing that's moving. And it transfers all of its momentum to the other car. That actually should make sense because it's the same mass, so it has to have the same velocity. Is it mathematically possible for both cars to move in a way that you would somehow get it? Yeah, it mathematically, but there's other reasons that we'll explore in future units that explain why this has to be the only result. Now let's think about when I had this is the more massive car and this pushed through. So what I would have, let's actually write it down, is I have two mass units going at some velocity forward, right? So this is just of the blue car. But then on the other side, I have the mass of the red car times the velocity of the red car plus the mass of the blue car times the velocity of the blue car. And that blue car, let's just kind of do it this way, is 2m, and this is just m. All right, so that blue car has to slow down and still go forward, and then you have this red car add to that so that we have it equal. And what if you switch it the other way? Why does this actually have to go backwards? Well, the reason it has to go backwards is I have one mass unit for the blue car times the initial velocity of the blue car, and that's going to have to equal the two mass units from the red car, and it has a certain speed, and this is a positive speed, this is a positive speed, and then I have the mass of the blue car, and that needs a speed too, so that's a blue car. But m to m, right? So if this moves forward at all, this needs to move backwards just to account for that. And we'll get into the mathematics of that in more detail. I'm not too worried about that right now. Just realize equal masses that collide with each other, so if one's moving and the other one's not moving, well, they'll essentially transfer their momentum from one to the other such that the velocity ends up being the same and the car stops. You have a heavier, more massive car, so a more massive car go into a lighter, less massive car, well, they both go forward. And actually the lighter car goes faster. And then you have a lighter car, like this one right here, less massive, go into a more massive car that's stationary. Well, there's so much inertia here that this actually bounces off and goes the other way. And all of this can be explained with something known as conservation of momentum, which we will do in a more quantitative way in another video. All right, so we just took a look at what happens in elastic collisions where carts bounce off of each other. So what I want you to think about now is what happens when one cart is pushed into another stationary cart and they bounce off of each other. And so I really want you to think about the speed and direction of each cart when you answer this. So what happens when both carts have the same mass? What happens when the pushed cart has more mass, and what happens when the stationary cart has more mass? Hit pause, think about those answers, unpause when you're ready to reveal. All right, so as we saw in the video earlier, when one cart with the same mass of the other cart collide, it actually transfers its speed to the other cart in such a way that the moving cart stops and the stop cart moves. And this comes down to conservation of momentum again, where mass times velocity of that first cart, the only one moving, will equal the mass times velocity of that second cart. And since they have the same masses,
they end up having the same speeds. When the push cart is more massive, well, now let's think about that. So when it's more massive, you push it into the lighter cart. That more massive cart is going to keep moving forward, but it's going to slow down because it ran into the other cart. The other cart is actually going to end up going faster than the cart that was pushed into it because it is a lower mass. Now, what happens when the stationary cart is more massive? Well, when you push that less massive cart into it, it actually bounces backwards and it pushes that stationary cart forward at a slower speed than it was traveling at. Now, all of this comes back to conservation of momentum, which we will look at in a more mathematical way later.